Okay, so we're at 2.3.1 talking about conditional Gaussian distributions. So this is something that's going to be useful later on. It's just good to know about it now, and you can come back to this later when you encounter situations. And those situations are going to be when you have, again, as we're going to see here, so you're going to have variables that are jointly Gaussian. You'll kind of know this, and then you want to condition on one of them. So, what if maybe let's just get into it and you'll see what I mean. And so I think, again, it's good when we're going through this section, just make sure you can follow along with the derivations and what's going on. You don't need to remember the exact formulas, but just remember kind of the key takeaway, which is that if two sets of variables are jointly Gaussian, then the conditional distribution of one set conditioned on the other is again Gaussian. This is going to simplify a lot of our work later on. So for now, just kind of go through this. Make sure you know what's going on. Don't worry about memorizing it, and you'll get plenty of opportunities to work with it later on. Okay, and then similarly, the marginal distribution of either set is also Gaussian. That's what we're going to talk about in the next section. Okay, so let's try. So we're going to work on, in this particular section, we're going to be working on the conditional distribution. So let's just see what we mean. Suppose X is a d-dimensional vector with Gaussian distribution X, the normal distribution of X given mu and some covariance sigma. And now we're going to partition X into two disjoint subsets XA and XB. Okay, so we've got this kind of, by design, we've got this jointly Gaussian thing. And now we're going to split it into two parts, and we're going to condition, we're going to see what happens, what we know about one part given I tell you the value for the other part. So without loss of generality, we can take x of a to form the first m components of x, with x of b comprising the remaining d minus m. That just means relabel things so that we've got xa, the bit you're interested in is going to be the first m, and then the rest is going to be the remaining indices. Okay, so now our x variable is going to be partitioned this way. Then we can also define corresponding partitions of the mean vector given by mu of a and mu of b. So we just use the same indexing to get the corresponding means. And then we set up the covariance also in the same way. So remember, the elements of the covariance are going to be the covariances of the individual elements of X. So if you rearrange X, then you will also rearrange the means, and you also rearrange the covariances. So in general, it's going to look like this. We've got the covariance of the elements of A with itself, then the covariance of A with B, B with A, and then B with B down here. And now, because the covariance matrix is symmetric, we know that that sigma, this covariance C, sigma B of A, is just the transpose of this thing on the top. So we talked about this last time. The covariance matrices are symmetric. Okay, and now we're also going to see that so in many situations it'll be convenient to work with the inverse of the covariance matrix, which is the inverse of this whole thing, and this is called the precision matrix. And the reason why we're going to do that is, as he says, some of the properties of the Gaussian distributions are just more naturally explained in terms of the covariance, whereas others take a simpler form when viewed in terms of the precision. So it's useful to be able to go back and forth between these two. In the same way, we can actually partition the precision matrix. Just the only really important thing to remember. So this is going to be symmetric. So sigma, I guess that's lambda b of a is going to be the transpose of lambda ab, etc. But the really important thing to remember is that, in general, this precision here, so lambda AA, is not the inverse of sigma AA. It actually only happens if, and you'll see in the expressions, it only happens if these off-diagonal elements are 0, and in general they won't be. So it's just really important to remember that inverting, you can't just do it blockwise. It's actually a bit more complicated, and we'll see what it looks like. So let's just highlight this, and simply not given by the inverse. In some special cases it will be, but in general it won't. So just keep that in mind. Okay, so now let's continue. Okay, so now let us begin by finding an expression for the conditional distribution P of XA given XB. Let's just highlight that, because that's going to be what the whole game is going to be about in this section. So we're given x of b, it's going to be some value, and now we want to know what is the distribution on x of a. Okay, now it says from the product rule of probability, we see that this conditional distribution can be evaluated from the joint distribution, so P of x a, this is what we already have, simply by fixing xb to the observed value, so that's what we're given, and normalizing the resulting expression to obtain a valid probability distribution over x of a. Okay, so the idea is that, and that's essentially what happens, right? So, you know, if we wanted to go through the normal machinery, you would get P of XA given X of B is equal to P of XA, X of B, which we have, divided by P of, you know, X of B. So this thing at the bottom, you know, we fix xb to be whatever it is in the joint distribution, and then we have to normalize that joint distribution appropriately to get the conditional distribution. But there's actually kind of there's often a much faster way of doing things. So and that just has to do with working with what's going on inside the exponential, and looking at the form it's going to take, and noticing that, hey, that's kind of the form we expect for a Gaussian, and then just manipulating that little part of the expression to figure out what the mean and the covariance is. So essentially, we're going to go in two steps. You know, the steps are going to be one, realize that Pxa given xb is Gaussian, and we're going to do that in a second, and then figure out what the mean and covariance of that are, rather than kind of doing the normalization directly. Figure out mean and covariance of the conditional distribution. So that's what we're going to do. It's a very useful trick to know. I use it quite frequently. And it's really simple. So let's get into it. Okay. So it says, instead of performing this normalization explicitly, we can obtain the solution more efficiently by considering the quadratic form in the exponent of the Gaussian distribution given by 2.44, and then reinstating the normalization coefficient at the end of the calculation. So essentially what he's saying is, like, let's just look at, so this is what's going on into our joint distribution. So it's got this form. And now what we're going to do is we're just going to set, well, xb is given to us. So xb is going to be some number, or some vector, basically. And we're going to see, well, you know, what's left, we're going to view it as a function just of x of a, because if we look at this is going to be supposed to be just a function of x of a, with xb being a constant. So we're going to view this exponent in the same way. Everything else in the probability distribution is a normalizing constant. We'll worry about that later. We're just going to see, well, what is the form that this is going to take? And if you take a look, you'll see that it's actually just also a quadratic form in x of a. So, you know, there's x of a being multiplied by itself, and then there's x of a. Now remember that x of b is now a constant, so this is again, so now it's a linear term in x of a, and then some constants. So this thing is again a quadratic form, and so we know the probability distribution will be Gaussian. Now one thing I just want to point out, and notice that we have switched to the notation here, so now we are actually using the precisions here. So that's going to be, we're using the corresponding elements of sigma minus 1. So just keep that in mind. You'll see that as we go. So we're just using the corresponding blocks of this thing. So this is going to equal to sigma minus 1. So you know, the bits of that are going to interact with x of a it's just going to be this component. The bit that's going to interact with x of a and x of b is just going to be that component, etc. One other cool thing to notice, to kind of help you when you're writing these expressions, is notice that the indices on lambda tell you the indices of x to use. So when it's AA, you see that it's x of a, mu of a. When it's AB, you see one of them is a, the other one is b. BA is vice versa. And because this thing is symmetric, you don't have to worry about getting the order right. The answer will be the same, whether x of a is on one side or the other side, and whether you put it down twice in one direction. Because it's symmetric, it shouldn't matter. But yeah, just make sure that you've got the A's. The A's are lining up here, the B's are lining up there, the B's are lining up here, the A's are lining up there. And so if you flip them around, as long as you flip the lambdas, it should be fine. Okay, and then finally we've got this final term at the end, which is B's and B's lining up here. Okay, cool. So that's going to be all we've done so far. We've just expanded this this term in the joint distribution. So we've looked at P of x, which was this joint distribution, and we can see that, okay, so it has this form, and we said, okay, now if x of b is constant, what is this? How does this look like as a function of x of a? And we see that it's still a quadratic form. So this is again a quadratic form corresponding, and hence the corresponding conditional distribution will be Gaussian. So that's like a real lifesaver. That when we notice that, we see that, okay, our life is easy, because now we just need to figure out what the mean and the covariance are. But now you say, well, how are we going to do that? Well, we can essentially do it by inspection. So this is an example of, so we said this is an example of a rather common operation, something called completing the square. This is a really useful thing to know about. It's very simple, and it's like really, really useful. It comes up all the time. In which we're given a quadratic form to finding the exponent terms in a Gaussian distribution, and we need to determine the corresponding mean and covariance. Okay, and since such problems can be solved straightforwardly by noting that the exponent in a general Gaussian distribution can be written as, so what we're going to do here now is we're going to just expand this, and you'll see that when you actually expand it, you'll get, you get two terms basically. You'll get a quadratic term in x, and then you will get, and the thing is that what's sandwiching the x's there is going to give you the precision that you're interested in. And then you're going to have a linear term, and the thing that's multiplying x by is going to be related to your mean. So this first term gives you your precision, and then this term gives you something proportional to your mean. So essentially then you first figure out what this is, and then you look at the linear term and you extract what that is. That's all there is to it, and it's just really, really useful. And here it says, look, const denotes terms that are independent of x, and yeah, we have made use of the symmetry of sigma. Okay. So now, for example, for us, those const terms are going to be things that only involve x of b. So like this is going to be hanging out in const. Thus, if we take our general quadratic form and express it in the form given by the right-hand side of 2.71, we can immediately equate the matrix of coefficients entering the second order term to the inverse covariance matrix. That's what we just said. So we just look at anything that's kind of quadratic in x. That's going to be that's going to give us our precision that we're after. And the coefficient of linear term to sigma minus 1 times mu, from which we can obtain. So this is kind of a really important, really useful trick. Make sure you know about this section. It's just very useful throughout. It will save you a lot of work, basically. Okay. Now let's apply this procedure to the conditional distribution P of xa given xb, for which the quadratic form is, okay, so we will denote the mean and covariance of this distribution by mu of a given b and sigma a given b. So that seems like useful notation. Okay, so now let's say consider the functional dependence of 2.70, so this thing, on x of a, in which x of b is regarded as a constant. If we pick out all terms that are second order in x of a, we have, and so essentially, look, if we look at this thing, the only second order terms are gonna be contributed from this part of the equation, and we can see that it's going to be this multiplying this, right? So the only the only second order term within x of a, that x of a is our variable now, is this thing. So we immediately see just by inspection that the covariance that we're interested in, this conditional distribution, is just the inverse of that, and this is exactly. It was exactly this observation, right? So we looked at this. So we're looking for a general, for the Gaussian, and the Gaussian, the quadratic term multiplies the precision, and we see that, okay, so in our expression, these x of a's are multiplying that precision lambda AA. So therefore, our covariance is just the inverse of this. Same way that our covariance there would be the inverse of that. Okay, so that's really useful. We can give ourselves a tick mark for that. Okay, great. And now we're going to look at the linear terms. So now we're just going to go back up to this thing, and you're just going to collect all the linear terms, right? So let's see. There's going to be, let me change colors to like orange or something. So there's going to be x of a is going to be, so there's going to be one here, right? So that's going to be multiplying this. So that's going to be 1. There'll be the same thing in transpose. So it'll be twice of that. And then I think that's about it. So let's have a look. Yeah, just because if you just work it out, you'll see that this is going to be the linear term. So, and linear means it just has one x of a in it. It can have other things in it, but it has to have at least one x of a. It has to have exactly one x of a in it. Xa multiplying. So it's linear in xa. Okay, and we've used we always just keep in mind the symmetry thing, because that's going to simplify the expressions. Okay. So now for our discussion of the general form 2.71, the coefficient xa in this expression must equal the precision to the -1 times mean. So again, we're just saying, look, we've looked at in Gaussians, whatever is multiplying the linear term is the precision times the mean of the distribution you're interested in. And we already have the precision. We just got it. So this will allow us to get the mean. So essentially what he's saying is, look, this linear term, so that's going to equal to, the precision we got, I guess is going to be -1 times mu of A given B. So now if we multiply this on the left by this, then we will just get this out, which is exactly what we're doing. So here, notice that this sigma, this covariance of A given B is now multiplying, this linear term. So that term has just come down. It's exactly the same, and now we're multiplying it on the left by this covariance. And then we use the fact that sigma A given B is equal to what? The inverse of that precision. So that's just going to cancel this initial term, and then we get it hanging out, multiplying the other precision. Cool. Okay, so one thing to just point out, which is interesting, is that you can think of this. Well, what's essentially happening is that this mean is the conditional mean is the marginal mean, the original mean you start with, plus this correction based on the deviation of xb from its mean, and it's linear in xb, so it's kind of a linear update that's happening. And he just touches on that later. We'll see much more of this in, I think, by the sounds of it, in chapter 8. All right, so the results are expressed in terms of the partition precision matrix of the original joint distribution P of xa. So essentially saying, look, this covariance is, in terms of, it's coming in terms of this, the precision of the original matrix. This mean update is, again, in terms of precisions. Can we talk about it now in terms of covariances? We can also express these results in terms of the corresponding partition covariance matrix. So let's highlight that just to say that's an important bit. That's what we're going to be doing. We make use of the following identity for the inverse of a partition matrix. Again, this is like, you don't have to memorize this. You can just look this up all the time. But we're going to need it. So where we have defined M is going to equal to A minus, this complicated thing. So it's like this minus the inverse of that times B times C. So the Schur complement, so this thing without the inverse is a Schur complement. Again, you don't need to memorize it. If your work makes you use it all the time, you'll just memorize it naturally. So don't worry too much about that. But just know what this is. Okay, so the quantity m to the -1 is known as the Schur complement of the matrix on the left-hand side of 2.76. So that's this thing with respect to the submatrix D. So you can do it for, I guess, with respect to the others as well. Okay, using the definition, so this was just a definition of where these lambdas came from, and making use of 2.76, we see that, we're putting A in there, B in there, etc. We see that sigma AA is going to equal to the inverse of the Schur complement. Okay, you can just think, I think this is, we don't necessarily have to know exactly what it's called. You can just apply this formula. You can say, look, you went on Wikipedia, you found this formula, you put in sigma AA, sigma AA, sigma AB, whatever, sigma BB. You wanted to inverse it, and it said, well, to invert it, the inverse of that is going to have this term at the top left, and the top left, that's the inverse of something called the Schur complement. Okay, so, and that's exactly what we see here. So if we plug in all of that stuff, the covariance that we're interested in, the first one we're interested in, the precision is this one. And if we look at this expression, what it looks like, we put in A, which is sigma AA, B, which is sigma AB, D minus 1, which is sigma BB minus 1, and then what's the other one? C, which is sigma BA. So that's all, and we just invert that according to this to get this expression. Okay, and then similarly, sigma AB is going to be this thing up here. So you're going to have to just kind of plug that in. So yeah, so I think it's I wouldn't say I don't find these expressions intuitive. If I find a good intuition for them, I will relate it to you. It's just good to know that just good to know they exist. What it's called, you can just look it up. So if you want to express these expressions in terms of your original covariances, this is the way you do it. Okay, so from these we obtain the following expressions for the mean and covariance. So again, the mean update is equal to the original mean plus your original covariance AB times the inverse of bottom left corner plus times this correction. So essentially you're taking the original mean and then doing a correction that depends on where x of b actually fell. Similarly, you'll see that this covariance is again being updated according to, there's some initial adjustment of, there's some initial value you had, the marginal covariance. We'll see that actually is the marginal covariance in the next section. But then being adjusted by the covariance of B and the covariance of A and B. So there's a kind of a correction there. Now what's really interesting is we said the conditional distribution takes a simpler form. So before we get that, so comparing 2.73 and 2.82, we see that the conditional distribution takes a simpler form when expressed in terms of the partition precision matrix than when it's expressed in terms of the partition covariance matrix. And essentially he's just saying that, well, if you look at the update to the precision, well, you have the mean, you have this deviation being multiplied by a couple of precision terms. That's not necessarily any simpler, but the covariance is quite simple in terms of the precision. So that's kind of one reason to be able to, one way it's useful to be able to work in both ways. And then we'll see in the next section that for the marginal distribution, it's actually simpler to just work in terms of the covariances, because you'll get the very intuitive result that the mean and the covariance, the marginal distributions, are just this and this. But we'll get to that there. And the final point is that the mean of the conditional distribution P of xa given xb is a linear function of xb. So this is very cool, right? So if you have these, if you got these expressions and you get a new xb, your update to your mean after observing xb is just linear now, which makes your life a lot easier. And the covariance is independent of x away. So it should be is a linear function of xb. And the covariance is independent of x of a. It's also, I wonder whether he means x of b as well, but because it is independent of both of them as well. Anyway, maybe we'll see that when we talk about this linear Gaussian model in 8.1.4. All right, so I think that was that's all there is in this section. I think the main thing, I think the main point that the main takeaway is that if they're jointly Gaussians, then conditional distribution is again Gaussian, and we'll see the marginal distribution is also Gaussian. So when you're working with jointly Gaussian variables, just remember that you have these nice properties. You can come back here and figure out exactly what they are, but you have these nice properties that'll make your calculations simpler. If you're trying to implement it in the circuitry, it'll also be simpler. And then the other thing that we talked about, which was very useful, was the completing the square. So this thing is very useful. So just being able to just look at your the quadratic forms, being able to recognize that, hey, I'm dealing with Gaussians here, and then using completing the square simply by just essentially template matching, being like, well, if it's Gaussian, well then this is where the precision would show up, this is where the mean would show up, and just reading that off more or less. So that's that. And then finally, we actually got our expressions for the means and the covariances. And then if you actually want to express them in terms of the covariances, then you just use these inversion formulas, and we encounter the Schur complement. Again, so whenever I've used this, I didn't need to know what it was called. I just simply plug this in. But maybe we'll see that it'll come up often enough that we should memorize it. So I guess we'll see that as we go. Great. So hopefully that was useful. Again, it's just more practice working with Gaussians. And the next time we'll talk about the marginal distributions, and we'll see what that is and how to compute it, and we'll get a very nice intuitive result. So I hopefully you learned some stuff. Please let me know if you did or if you didn't, or there's a mistake somewhere. I'm happy to fix that. And I hope to see you in the next video. Bye.